Hi guys, I want to look at the electric field for a disk of charge. So we looked at the electric field of a ring of charge, and what we said about the ring of charge is, okay, we looked at a ring of positive charge, right? So we had some positive charges on that ring, like this, and we said this ring has a center O, it has a radius, that is its radius, and it's R, and we said there is a point P, that is a distance x from the ring of charge, and we say we isolated a charge that was there, which we called dq, and then this distance here was the square root of x squared plus r squared. Let me make that a small letter r. So we got that electric field as E equals, we said it's equal to K Q X over x squared plus r squared to the power 3 over 2. And we also wrote another form of it, which said so it was K lambda x s, but s is 2 pi r because it's the circumference of that ring. So that was going to be 2 pi K lambda x r, right, over x squared plus r squared to the power 3 over 2. Remember what lambda is. Lambda is the linear line charge density, right? And it's given by lambda equals Q over L. In this case, our L was 2 pi r because we're talking about a ring of radius r. So that means Q was lambda times L. Hence, here we replaced that Q there with lambda times 2 pi r, which is our lambda times L. Let us now look at the disk of charge, right? So for the disk of charge, remember a disk is made of many rings. Let me just draw just a circle like this. If I were to put another ring here, just inside that circumference, and I keep doing that, maybe I do that starting from the center, going like this, right? I'm going to, if these rings are closely packed, then this thing is going to be shaded in the end. That's what's going to be to happen there. So that will be many rings of positive charge making up just a disk of charge. So it becomes a disk, it becomes a surface, an area, right? So I want us to now look at, so this disk is facing that way, so it looks like an ellipse because I want it to face that direction, right? So I'm trying to put that in 3D actually. So let us now look at the disk of charge. So it means we have positive charges on this disk. We have positive charges on this disk like this. We still have our point P. And this disk of charge is of radius capital letter R. Right? So let's put capital letter R for the radius of the disk. Let me just do this. And let me put R there. So that is the radius of the disk. So since a disk is made of many rings, it means the electric field of a ring of charge, which we got here, is very small compared to that of a disk of charge. What do I mean? It's like a drop in an ocean, right? So basically, if we then want to obtain the whole ocean, we need to count every drop that is in that ocean. right? So the ring is contributing only a small electric field to point P, right? But if we now consider a disk, we are now considering all rings that make up that disk, right? So it means the electric field due to a ring is only a dE, right? So we can now say that electric field that we have there for a ring of charge, we will now say that is our dE. Let me put that in white. So that becomes our dE, right? And it's equal to what? K dq with an x here, so it's kx dq, right, over x squared plus r squared to the power 3 over 2, right? So now that we have an area, this is now an area, a disk is an area, right? So we still have, everything else is still the same, everything else is still the same. But now this is x squared plus r squared, isn't it? That is now x squared plus r squared. But anyway, we know what the electric field due to the ring is, right? So that's what we are interested in. So that is still our x. And what's going to happen now is, we know this is an area. So instead of looking at the area charge density, the ring was a line. Because you take a ring, you can make a ring out of a straight wire. You can bend it and form a ring, right? So now that we are looking at an area, we have to talk about area charge density. So that means dq is no longer equal to lambda ds, right? dq, because q over, let me just rub this off. So q over a, charge per unit area, we call this sigma, which is the area charge density. So if we have dq over dA, that gives us our what? That gives us our sigma. So that means sigma is equal to, dq is equal to sigma dA, right? dq equals sigma dA. That's what it means, right? So dq is sigma dA, and what we can do here with this dA, we know that A, the area, is equal to pi r squared. So dA, if we take the derivative with respect to r, dA dr is equal to 2 pi r. That means dA, so dA is equal to 2 pi r dr, right? So that means there we can go and say dq is equal to 2 pi sigma r dr, right? So I now go back to our equation for the electric field, to our equation for the electric field. What are we going to do there? We're going to now replace dq with that thing there. So we'll go there and say dE is equal to what? Remember, this is also in the I-ahead direction, right? So it's in the I-ahead direction. That is why I put it as a vector A. That's going to be equal to kx, then we put a 2 pi r. So we're going to put a 2 pi sigma r actually. 2 pi sigma r dr. So it's 2 pi kx sigma r dr over x squared plus r squared to the power 3 over 2. So we integrate both sides. What's going to happen? If we integrate both sides and we are going from the smallest ring that we have to the largest ring that we have, which is the outer ring on that disk, which then gives us the radius of what? Of the disk of charge. On this side, we will get our E, right? Equals what? On that side, we are going to get, if let's look at the constants and what we're integrating with respect to. This whole thing, let me show you. These are all constants. X is also a constant, but R this time around is not a constant. We're integrating with respect to R. So what we're going to do is, we are going to say, we're going to put all constants outside. We'll have 2 pi kx sigma, and then we say over what? This thing here, we're not going to put it outside. Why? Because it has our R there inside. So we're just going to put 2 pi kx sigma outside. Then we'll have the integral from 0 to capital letter R of R dr over x squared. X squared plus R squared to the power 3 over 2. So what we're going to do now is, we're going to use integration by U substitution. If we let U equals, because we're integrating with respect to R and we have an R inside there, so we'll let U equals x squared plus R squared, right? That means du over dr equals 2R. That means du equals 2R dr, right? So we'll now say the integral becomes what? The integral there becomes, let's see. We will now have du over 2, or rather, what we can do, since we have a 2 here, we can put it back inside, so that we'll have a 2R dr there. The substitution will now be easier for us to make. So we are then going to replace 2R dr with du. So that means we'll have a 1 du over, that's going to be u, everything that's in there, to the power 3 over 2. That gives us the integral of u to the power of minus 3 over 2 du. And that integral there, we're adding 1 to the power divided by the resulting power. This is like minus 1.5 plus 1, it gives us minus half. So we end up getting something like this. And then what we can do here is, we can take that 2 to the numerator. So that half, if we cancel it, let's just write it on the solution side. That's going to be u to the power of minus 1 over 2, right? All over minus 1 over 2. So we're going to have something like this here, which then gives us minus 2 over the square root of u. And we can now plug in whatever we had there. So I'm just going to rub off the u substitution because this is calculus, right? So we have minus 2 over root u. We know what u is. So we have E, right, equals minus 2 pi k x sigma, right, over the square root of u. But what is u? U is x squared plus r squared. So this is what we will get in the end, right?